In the cross-Claisen reaction, now we have a reaction that's between maybe two different esters, or it could be a ketone and an ester. So let's start with an example where we have two different esters. If we look at these, this was set up such that we don't run into a mess of products like we saw at the start of the crossed aldol reaction, because what we have is one ester that has acidic alpha protons. The other ester has no alpha protons. So that makes this the automatic electrophile. And then the methyl ester on the left will end up being the nucleophile. In this case, we are using methyl esters. So that's why the base I used was sodium methoxide, because remember, you want your base to match your OR groups of the ester. So we have that followed by dilute acid. If we're just predicting the products for this, it's quite simple. So what you want to do is find the ester that's going to be the nucleophile. Think about that reacting with the base to give the enolate. Then we'll react this with our second molecule of ester. I'll draw it in a different color so we can better keep track of it. And if all you want to do is predict the product, we can make this very easy. Just think about your nucleophilic enolate attacking to bond to the carbonyl carbon, losing the methoxy group. And then the product we get we'll have a new bond. It's a double bond O and the phenyl. And that's the final product of the reaction. So this is a good way to predict the products. Just keep in mind, and this is very important, this is not the official reaction mechanism. This is just a trick to predict the product of the reaction. We talked through the entire mechanism, and it's the same as for the regular Claisen reaction, where you have several steps. And as practice, it would be good for you to start with this enolate and work through the entire mechanism for this to make sure you know all the steps that are involved. Just for reference, if you did work through the mechanism, here I have the full reaction mechanism for that reaction drawn out for you, starting with our enolate formation, adding to the carbonyl, all the steps including the acid-base reaction, which is the driving force. So if you need to, you can pause and take a look at that. We can also do a Claisen reaction between a ketone and an ester. In this case, the way that we decide what's the nucleophile and what's the electrophile is through acidity and pKa's. The ketone, those alpha protons have a pKa of about 20. We learned previously that the ester is a bit less acidic because these lone pair electrons are donating. That decreases the acidity. So this has a pKa of about 25. So it's easier for the base to deprotonate the ketone, making it the nucleophilic enolate, and the ester will be the electrophile. So we're going to go through this reaction. We won't go through the full mechanism. We're going to take our shortcut. But what you can do is start by drawing your enolate. Then we'll draw out our ester, which is the electrophile. Again, this isn't the true electron pushing mechanism, but to predict the product, just take your enolate, add that to the carbonyl carbon, and we could lose the O-ethyl group. So now when we draw the product, here's our new bond to the carbonyl carbon, and that still has the ethyl group attached. The product of this is a 1,3 diketone. Or you could also call that a beta diketone. You could also do a directed version of this. It's very similar. We're just going to change our base to LDA. So start with the carbonyl compound you want as the nucleophile and add LDA, just like you did in the directed aldol reaction. That will form 100% of the enolate. Then in the next step, we can add our ester that we want to see electrophile. And then finally, this would need an acidic workup. In the end, we get the same product.